In our last lesson, we talked about the graphs of sine and cosine functions, and we only shifted them with a change to the period as well as a change to the amplitude, which was horizontal dilations and vertical dilations. But today, we're going to continue to do different types of transformations to these graphs of sine and cosine. So thinking back to other things we know about transformations of functions, the graph of the function y equal to f of x minus d is translated horizontally compared to the graph of y equals to f of x. The translation is to the right d units if d is greater than 0, and it's to the left the absolute value of d units if d is less than 0. So what we can think about here is that if you see x minus d in the equation, your graph is going to move to the right. And if you see f of x plus d, because that's a minus minus d, your graph is going to move to the left. Now with circular functions, a horizontal translation has a different name, kind of like amplitude and period. We don't just call those the dilations. This is going to be called a phase shift. In the function y equals f of x minus d, the expression x minus d, which is the stuff inside the parentheses, is going to be called the argument. And a phase shift is always going to be d divided by the period, and this is especially important when you don't actually see the period listed, meaning if you don't actually see a number in front of the parentheses for x minus d, then the phase shift would have to be divided by the period, which is that number in front of the parentheses. Now, the first few examples, we're not going to have to worry about that, but I'll point it back out to you whenever we get to a problem with that. So we're going to be graphing y equals to sine of x minus pi over 3 for one period. Now, if you think about the steps that we took last class to graph these functions, we're going to follow the same idea. And as we get more comfortable with this, you may not need the table to do this, but while we're learning, it'll be helpful. So what we're going to do is we're going to take that argument, x minus pi over 3, and we're going to figure out what its new period would be. A typical period for a sine function is between 0 and 2 pi. But since we are shifting this graph, we have to shift both of these by adding pi over 3 to both sides. So 2 pi plus pi over 3, remember 2 pi is the same as 6 pi over 3. So this has actually become 7 pi over 3. So my one period for this function is going to occur between pi over 3 and 7 pi over 3. So to figure out what the other boxes should be here for my different intervals, I'm going to put 7 tick marks on my x-axis. 1, 2, 3, 4, 5, 6, 7. This is 7 pi over 3, and this is pi over 3. So we're not going to start at anything on the y-axis here since it has been shifted. Now we know halfway in between these two, I'm sorry, my dog just whined in the back of this video. Halfway in between 1 pi over 3 and 7 pi over 3 is 4 pi over 3. So that's going to be the value in the center here, halfway in between those two. And if we go halfway in between 1 pi over 3 and 4 pi over 3, we're actually going to be here in the middle of the pi over 3s at 5 pi over 6. So this becomes 5 pi over 6. And if we do that on the other side, it's 11 pi over 6. Because it's halfway in between these two values. Okay, so we have our x values that would designate the different subintervals. We're going to subtract pi over 3 from each of them, and wouldn't you know it, pi over 3 minus pi over 3 is 0. 5 pi over 6 minus pi over 3 becomes pi over 2, and then we get pi. These values should look really familiar to you. These are always, if you've done this right, going to be your quadrantial angles, because then we can do the sine of those quadrantial angles very easily. That is your midline, your maximum, your midline, your minimum, and a midline. And now we're able to plot these points with the correct amplitude. Since there's no vertical dilation here, this is going to be an amplitude of 1, the typical range of the sine function. But we're not going to start at the y-intercept. We're going to start at 0, or pi over 3, 0, 5 pi over 6, 1, 4 pi over 3, 0, 11 pi over 6, -1, and then 7 pi over 3 back at the midline. And so there, if we play connect the dots, there we have our sine function that has been shifted pi over 3 units to the right. Moving on to the next example, if we look at graphing y equals 3 times the cosine of x plus pi over 4, again, we're going to figure out what that argument does to our interval for one period, our domain for one period. Typically, cosine, like sine, is between 0 and 2 pi. If we subtract pi over 4 from both sides to solve this double inequality, we end up noticing that our x value is going to be between negative pi over 4 and 7 pi over 4. Because, okay, 2 pi is 8 pi over 4, right? So we subtract 1, it's 7 pi over 4. So we know our furthest that this is going to go for one period is 7 pi over 4, coming from negative pi over 4. If I go ahead and plot those points, that's going to be, here's negative pi over 4, then I have 0, then I have a 1, 2, 3, 4, 5, 6, 7 pi over 4 occurring right here. Now, if I look halfway in between these values, you can count on the x-axis there. It's going to end up being at 3 pi over 4. So we add that both to our chart as well as our graph at 3 pi over 4. Now, halfway between negative pi over 4 and 3 pi over 4 is positive pi over 4, right here. And then halfway between 3 pi over 4 and 7 pi over 4 is 5 pi's over 4. And so we can add that to our graph as well. Now, if we take the argument and we do x plus that value, the x plus 4, again, you should notice that these are always becoming the quadrantial angles. That's because those are the angles for sine and cosine that give us our max, min, and middle values. So we take the cosine of those, it's going to be 1, 0, negative 1, 0, and 1, but this has been vertically dilated by 3. We have changed the amplitude, so this actually becomes these output values. So when we plot these points, here's the value 3, here's the value negative 3, we can go ahead and plot the points. So at negative pi over 4, I'm going to be up at 3. At pi over 4, I'll be at 0. And then negative 3, and then back at 0, and then back up at 3. So if I play connect the dots here, our graph for this cosine function, which is shifted to the left, will look something like this. Again, both of these functions have been horizontally translated, but that for us means, again, that we are using this phrase phase shift to talk about how it has been moved side to side. We are changing the phase shift for the function. Let's go ahead and do one more, getting a little bit more complicated. For this graph, if you notice, the argument looks a little different. The argument of this function, negative 2 cosine of 3x plus pi, doesn't have a double set of parentheses to show us both the change to the period, the horizontal dilation, as well as the phase shift. So we actually have to do, it doesn't feel like work really, but we have to do a little bit to understand what's happening here. So if I rewrite this function, seeing the double parentheses here, it would be like I'm factoring out the number 3. And when I factor out the number 3, 3x divided by 3 is x. That's what we want, the x to be by itself. And pi divided by 3 is simply that, pi divided by 3. So when I do this one, I know that I'm not only going to have a change to the phase shift, I'm also going to have some sort of change to the period of the function, so it just gets a little bit more complicated. But let's figure out our values for one period. I know the question says 2 periods. We will just repeat the shape. But if we find out the values for one period, we're going to take the argument, the whole argument, 3x plus pi, and we're going to solve for our new domain, since it does have a phase shift, which means we're going to subtract pi from both sides. We'd end up with 3x still in the center. 2 pi minus pi is pi. And then we divide by 3. So I have negative pi over 3 less than or equal to x, which is less than or equal to pi over 3. So at these values, I should start and finish my first period for this function. So this would be at negative pi over 3 and end at pi over 3. Again, this is just one period and we will graph 2, but we just have to repeat the numbers. Halfway in between negative pi over 3 and pi over 3 is 0. Halfway in between negative pi over 3 and 0 is negative pi over 6, and thus positive pi over 6. Now I know I'm going to get to the graph here soon, but if we just look here at the table so we know what values we're going to do. The first table that you're going to type in here, the first thing you're going to put in here, is x plus pi over 3. Notice that that is the argument that has already been factored. And I want to do this because it'll lead me to those quadrantial angles a lot easier. So negative pi over 3 plus pi over 3, that's 0. Then I would get pi over 6. Then I would get pi over 3, because we're just adding pi over 3 every time. Then I have pi over 2. And then I have 2 pi over 3. So if I take this and I multiply those values by 3, since that's the change to the period, 3 times 0, still 0. 3 times pi over 6 ends up giving you pi over 2. Oh, that looks familiar. Pi over 3 times 3 is pi. Look at that. Our quadrantial angles have shown back up for us because these are going to be the easy values to take the cosine and sine of. So if we do the cosine of this value, and I'm going to cheat and just do this. Cosine of 0 is 1, then you have 0, then you have negative 1, then you have 0, then you have 1. But we're going to take this and we're going to multiply it by negative 2 because we are having both a vertical dilation, a change to the amplitude, as well as a reflection, which means my output values are negative 2, 0, 2, 0, and negative 2. Okay, it gives me all of the values for one period of this function, but we know we're going to graph 2. So we do need to come over to our graph and add the tick marks that make sense. Now, I'm not going to lie to you, I should have scooted this graph over a little bit, so if it doesn't bother you too much to have like whiteout and or just like a messy part of your notes, I would take this y-axis and I would actually scoot it over a little bit so that we can have some negative values on our graph that makes sense. So I'm just scooting it over slightly so that I have more room in the negative values. So if I do these tick marks, I'm going to have negative pi over 3, negative pi over 6, and then pi over 6, and then pi over 3. Since I want to graph 2 periods for this function, I need to extend this distance. Now, if I notice, the period of this function from start to finish is 2 pi over 3. So I know if I add an entire other subinterval, it'd be pi over 3 plus 2 pi over 3, which is 3 pi over 3, or pi. Halfway in between 1 pi over 3 and 3 pi over 3 is 2 pi over 3. And then halfway in between those values is going to end up being pi over 2 when you reduce that fraction, and 5 pi over 6. So now I have all the tick marks. On the x-axis, I will need to draw this function. I also know that I'm going to have an amplitude of 2, and I can begin graphing my function. So we know that the first coordinate based on the table that we have is negative pi over 3, comma negative 2, and then 0, and then 2, and then 0, and then negative 2. And I'm just going to repeat that pattern for another period at each and every one of these tick marks, which is why we make sure we have them. Now that we have 2 periods graphed, we can play connect the dots and draw our cosine function that has been shifted with a phase shift of pi over 3 to the left. It is a higher frequency because our period is 2 pi over 3 instead of 2 pi. And it has an amplitude or a vertical dilation. Now, not only can we move things sideways, creating a phase shift, obviously we can also move these graphs up and down with regular vertical dilations. A graph of the function y equals f of x plus c outside of the parentheses is translated vertically compared to the graph of y equals f of x. The translation is up c units if c is greater than 0, and down an absolute value of c units if c is less than 0. So if you see plus a number at the end or at the beginning, then you're moving it up. If you see it moving down, then it is minus c. Now here's something that's important. This textbook doesn't use this phrase, but in AP Pre-Cal we do, and I think it's very helpful. C creates what's called your midline. Your midline can also be found in a word problem from taking the max plus the min and dividing it by 2. Now this looks familiar because it's very, very similar to the equation for the amplitude. It's just that it is the average of the max and the min instead of the difference of the max and the min. So there's a plus sign in this formula instead of a minus. That creates the midline, or where all of our middle values will be for the function as it waves up and down. So let's see what this looks like. We're going to be graphing y equal to 3 minus 2 cosine of 3x, again, over 2 periods, so the table will help us with 1, and we can just repeat the phrase. Some things I want you to notice is that because of the 3 value in front of the x inside the cosine function, that means that the period of this function has changed from 2 pi to 2 pi divided by 3. Because we don't have any plus or minus values inside the cosine function, there is no phase shift. So we're not going to be scooting this left or right. It should start on the y-axis like everything did last time. Okay, so we know that the beginning of this graph is going to be at 0 because there's no phase shift, and the period is 2 pi over 3, so I know that those are my starting and ending values. Halfway in between them is pi over 3, halfway in between that, pi over 6, so if I add that again, it ends up being pi over 2. So that means that we need to figure out what to put in this table. Now, I want to start at the smallest or most inside of this function as possible, which means I'm just going to start by doing 3x. So 3 times 0 is 0, 3 times pi over 6 is pi over 2. Oh dear, look at that. Our quadrantial angles have come back, which are the easy ones again to do the cosine of. So when we do the cosine of 3x, moving out from this function, getting bigger and adding more things to it. Cosine of 0 is 1, and then 0, and then negative 1, and then 0, and then 1. But we're going to take that and we're going to dilate it and reflect it. So we're going to multiply that by negative 2, which means this is negative 2, and 0, and 2, and 0, and negative 2. But alas, we have a vertical translation here, We're going to change the midline, which means we're going to take all these values and we're going to add 3 to them. Now, why did I say add 3 when it's in front? Great question. I could rewrite this as 2 cosine of 3x plus 3. And that's where we're typically seeing the plus or the minus for these dilations. We're used to seeing them behind the function, but they can occur in front of the function. And since it's a positive 3, we're going to scoot the midline up 3. So negative 2 plus 3 is 1, 0 plus 3 is 3, 2 plus 3 is 5, 0 plus 3 is 0, and negative 2 plus 3 is 1. So these are the values I'm going to have along my graph. I find it easiest when we're graphing things with a changed midline to actually write my midline on the graph. So I need to go up at least 5, 1, 2, 3, 4, 5. But at the value of 3, I'm going to have the midline of my function occur. So I like to make these dashed lines. In later chapters, that might get confusing to have a dashed midline when we introduce vertical asymptotes. But for now, probably helpful for you to see that. So here's 1. That's our midline at 3, and then our maximum at 5. If we do our x-axis, since we want 2 periods, we'll go ahead and make halfway 2 pi over 3, which means this is pi over 3. And to save space, I'm not going to label those tick marks. But if we double that, it's 4 pi over 3. And in the middle of that is just pi, because it's 3 pi over 3. Obviously, there are tick marks in between here. So we start with our values. For the first period of this function, we know that since this is cosine, we're going to start at either a max or min, but my table says to start at 1. And then I'm at my midline of 3, and then I'm at my maximum of 5, back at a midline, back at a minimum, and then midline, and then maximum, and then midline, and then minimum again. So when we play connect the dots here, the cosine function that we have graphed will look something like this. It's been shifted up above the y-axis since we have added that 3 to the function. In example 5, we're going to be modeling temperature with a sine function. Now this data says the maximum average monthly temperature in New Orleans, Louisiana is 83 degrees Fahrenheit, and the minimum is 53 degrees Fahrenheit. If the table shows the average monthly temperatures, a scatter diagram for a 2-year interval in the figure strongly suggests that the temperatures can be modeled with the sine curve. Now I don't show you the scatter diagram, but if you notice, the temperatures get higher and then they get lower again. So we're going up and down, and this would repeat year to year. So it's a sine function. Using only the maximum and minimum temperatures, we're going to determine the function of the form a sine of b times x minus d plus c, where a, b, c, and d are constants. Things that we will need to answer this question is to remember what the a, b, c, and d stand for in this function. Now the a value here is your amplitude. since it's your vertical dilation. We had a formula for amplitude in the last set of notes that is the max minus the min divided by 2. Now the problem tells us that the maximum is 83, the minimum is 53, so if we subtract those, divide by 2, we get 15. The b value for this is going to be related to your period. Remember, it is 2 pi divided by the period, which we don't actually see here until you think about this problem. This is modeling temperature, and temperature kind of repeats itself every year. It's hotter in the summer, cooler in the winter, hotter in the summer, cooler in the winter. So the period of this function is going to be 12 months, which means that b ends up being pi over 6. The d value here is going to be the phase shift. So let's write that down just so we remember. This is the phase shift. So we need to know how far we have moved this function so that the midline is happening at time 0. Now it would be helpful to have that midline, so that's the c value here, the number that we've added or subtracted onto the end or the beginning, and midline we had a formula that it was the max plus the min divided by 2, the average of the max and min, which would mean we're doing 83 plus 53 divided by 2, which is equal to 68. Now to determine our phase shift, we need to figure out which month we are closest to 68. If you notice, April has a value of 69 degrees Fahrenheit. That's the closest we're getting based on our data here to the midline of 68. So we're going to estimate that our phase shift wants to happen when April occurs, and April is month 4 of the year. So again, our midline is closest, the value of 68 is closest to the average temperature in April, so we're going to phase shift our graph to where April is at the midline. Now that we have these values, we just need to substitute them into the function that we were given. So we would write the equation f of x equal to 15 times the sine of, open parentheses, pi over 6, open parentheses, x minus 4, close parentheses, plus 68. And voila, we have our model for the temperature annually in New Orleans. Now we were able to do this by hand, which is awesome. There is also a way to use the calculator and use a regression, as we've used them before, to do the same thing. However, it's going to return to you a different type of function because it's not going to necessarily show you the period and the phase shift separately as we see here in our double parentheses version of the sine function. If you use the sine regression, which is like typical regression features, you go to stat, you go to edit, type in all the values, then you'd go back to stat, arrow over to calculate. This time though, you're choosing option C, which says sine regression. So you have to scroll a little bit to find that. You'll store the regression in Y1 by typing alpha trace inner. Again, these are the steps we did for regressions before. You press calculate to get the regression. Now, I can't show you this because I don't have a way to show the calculator screen on this video, but you can follow those instructions. You use all of the data points for January through December, noting that in the formula, 1 is January, 2 is February, 3 is March, and all that stuff. And what the calculator will return to you, so please go ahead and do that, but you should get these values on your screen when you finish the steps, 15.8728, 0.480517. It says the C value is negative 1.8341 and the D value is 68.3850. Now these are not necessarily the same A, B, C, and D that your book uses for the sine regression up above. The A still matches up, the B technically matches up, but the C and the D are reversed. The D that you are using is actually the phase shift here for C. And the midline number you're using is here for D. So those letters are swapped in the calculator and the textbook. So just don't get confused about that. And this is actually a more accurate data for this function. Since we estimated the phase shift, we said 4 for the phase shift. It really is different when you do this by hand. So this is a more accurate graph using a piece of technology to do this, but it was cool. We were able to do it on our own. So again, this function would end up being 15.8728 sine of 0.4805x minus 1.8341. Scooting over a little bit. And all of that plus 68.3850. Obviously, pay attention to your rounding, as the textbook will tell you if it needs you to round. Now, a question I had when I did this problem was, how close were we? It's pretty obvious that the 15, pretty close. And then for our midline, 68, pretty close. But the numbers in the middle, how is that possible? So if we think about this, we wanted to see the b value and then see x and minus some other number. So obviously, if I divide both of these numbers by 0.4805, squeeze that number in here, and if I divide 1.8341 by 0.4805, as if I'm factoring that out, I end up getting 3.82. Okay. Now, we said that the b value would be pi over 6. Now, pi over 6 actually estimates to approximately 0.524. Check out that number. That's, close enough for us to be doing this by hand. And if you notice, our phase shift value we used was 4, and the calculator gives us 3.82. So our estimate, just by looking at the data, is really not that far off from the regression that we get when we do this by hand. With technology, which I think is really pretty cool.